So far, we did cover the conservation laws, continuity, momentum, and energy equation. It's now time to look into a full example, looking for the combined fluid flow and heat transfer at once. In previous recording, we did cover the Couette flow, which is one-dimension, steady, incompressible flow between two plates separated by a certain distance h. So just if you recall the problem statement here, the bottom face of these two boundaries is fixed, and the upper one suddenly will be pulled by a uniform velocity u, and this will drag the fluid in between and causing motion. And we looked to the hydrodynamics of this example, and we were able to prove the velocity distribution, or to develop the velocity distribution between the two plates, and we have shown that it's coming in a form of a linear equation between the two plates. So this is the y coordinate. So this is y equal 0, and the separation distance between the two plates is said to be h. So that's the Couette flow. Now we will add the thermal section, or the thermal effect, into this equation. So I'm going to assume that the lower plate is at temperature, say it's T naught, and the upper plate is at different temperature, say T1. And there is difference between the two temperatures. So we are expecting there will be some heat transport between the lower plate to the upper plate, but that thermal transport is highly impacted by the fluid flow in between. So now we would like to drive the temperature distribution. So the statement is to find the T as a function of y. So this is a very good example to show how we couple between the fluid flow and the thermal transport into the liquid. So again, like every time we give an example, we have to start with the governing equation. So number one, I'm going to start with the continuity equation. So we have partial rho by partial t plus partial rho u by partial x plus partial rho v by partial y plus partial rho w by partial z. It's equal to 0. Couette flow is simply one dimension, steady flow, steady, incompressible flow. There is no external driving force, so there is no delta P between the inlet and the exit. So the pressure gradient is 0, so there is no pressure gradient. Just keep all of this information in mind, because it's going to simplify the existing equation. Since we are doing steady state, this term will goes away. So this is 0 for steady. And since we are dealing with incompressible flow, I can take the density rho out of this equation. So I'm going to end up having rho partial u by partial x plus partial v by partial y plus partial w by partial z. It's equal to 0. And we know that since we are dealing with one dimension, I know that that partial v by partial y is going to be 0. Partial w by partial z will be 0. And these are because the one-dimension flow. So I'm going to end up having simply from the continuity equation that partial u by partial x equal to 0. And the physical interpretation of this condition here is that we are in a fully developed flow. We mentioned before, we have a flow over a flat surface. The boundary layer will form, and we know that velocity distribution will change. Maybe start like this, it's increased like this. Then, so the slope will continuously change of that velocity profile until that velocity profile actually will repeat itself. So the slope is not going to change at the wall. This means that we passed what we call the developing region of the boundary layer to the fully developed region. So that's the meaning of partial u by partial x is equal to 0. So this is the outcome of the continuity equation. So the next governing equation will be the momentum equation. And in this case, I will do the x momentum since we have only one dimension. So I'm going to need the x momentum equation. So the x momentum equation will be simply, again, remember, we have a steady flow, we have incompressible flow. So I'm going to end up having rho partial u by partial t plus u partial u by partial x plus v partial u by partial y plus w partial u by partial z. It's equal to minus partial p by partial x plus mu is constant, is not changing, partial 2u by partial x square plus partial 2u by partial y square plus partial 2u by partial z square plus rho and gx. Body forces is neglected since we are doing one dimension, right? So this means that v and w is 0, so v is equal 0. W is equal 0, so this term will goes away here. Then we know that partial u by partial x, this is equal 0 from the continuity equation, right? This is 0 for steady flow. So simply the left-hand side is totally 0, and there is no pressure gradient in Couette flow, so this is also 0. So I'm going to end up having only mu partial u2 by partial x square. We know that velocity is not changing in the x direction, it's changing in the y direction. So this is actually 0. And if partial u by partial x is 0, this means that second derivative also will be 0. And there is no z direction here. So I'm going to end up having from the momentum equation that partial 2u by partial y square is equal to 0. Then you integrate that equation. You'll get partial u by partial y is equal c1, and u as a function of y will be c1y plus c2. Then you use the boundary condition. Again, this is a hydrodynamic section here. I'm going to use that when y is equal 0. We know that the velocity of the plate is 0. When y is equal h, the velocity of the plate is uniform velocity u. And this is a linear distribution of the velocity. And you should end up having u as a function of y is equal u over h times y. So when y is equal 0, the velocity is 0. When y equal h, the velocity is going to be u. You can refer to the previous recording to see the full solution. We did the full solution analytically, and we also use the finite difference method to solve that Couette flow numerically as well. So this is what we got from the hydrodynamic section here. And we will see why this is really very important, because it's really the conservation laws, continuity, momentum, and energy equation are cross-linked by velocity. And it makes more sense when you are dissipating energy from the lower plate to the upper plate. Definitely the kinetic energy, the flow velocity, will impact the transport of energy from the lower side to the upper side and vice versa. So let's go for the energy equation. That's the third part. So let's list the energy equation here. It's rho partial E by partial T plus U partial E by partial X plus V partial E by partial Y plus W partial E by partial Z. that should equal to lambda partial 2t by partial x square plus partial 2t by partial y square plus partial 2t by partial z square. I should have also the other terms that I'm going to ignore, right? There is P nabla dot V, and there is no pressure gradient here. And also the internal heat source, rho Q dot, is neglected as well. So the only term that's going to remain here is actually mu times the dissipation function. Okay, now let's simplify the problem here. So this equation, this is going to be 0 for steady, right? We know that that's steady. We know that V is 0, W is 0, which means that this term is fully 0 and this term is fully 0. But also we know that there is no energy change in the x direction. All the energy will change from the bottom to the upper or the top plate. So that's going to be 0, no energy transport in x. I'm looking for the transport of energy from the lower plate to the upper plate, which means that I'm in the y direction. What else? Let me explain here. So let me put all the terms for those who's not really deep into that equation yet. I'm going to put all the equations here. I mean, all the terms of this equation here, plus that's going to be u partial p by partial x plus v partial p by partial y plus w partial p by partial z. This is a full energy equation here. This term is when you have internal heat source. This is 0, no source was mentioned in that problem. This is the electric and this is the body force. Focus on mostly the electric and magnetic field force, and that's equal 0. We solve steady, that's 0. And we said that in Couette flow, there is no pressure gradient in any direction. So 0, 0, 0, no pressure gradient, because we don't have external driving pressure source or flow source. So the whole terms here are 0. Now we're looking for the temperature change in the y direction. So this is equal 0, and there is no z direction here. This is equal 0. So I'm going to end up having actually lambda partial 2t by partial y squared. That's one term plus mu phi. So I will have 0 equal to lambda partial 2t by partial y squared plus mu phi, where phi is the dissipation function. Let's write down the dissipation function and see how it's going to be simplified. Dissipation function in the full format is 2 partial u by partial x squared plus partial u by partial y squared plus partial u, that's v, and that's w by partial z squared, plus then you take partial v by partial x, so this will be partial u by partial y square. Then you take the v relative to the z, so this will be partial w by partial y square, plus you'll take u relative to the z plus partial w by partial x, that's square. Then we have minus 2/3 partial u by partial x plus partial v by partial y plus partial w by partial z. So this is the full dissipation function here. Now let's see how we're going to simplify that. So partial u by partial x equal 0, right? This is from the continuity equation. V and w, v is 0, w is 0, so this term goes away. Again, w is 0, w is 0, v is 0, v is 0, w is 0, v is 0, right? This is 0 from continuity. So this term totally now is 0. There's no change of u in the z direction. I have only one dimension flow. So I'm going to end up having the heat dissipation function to be simply partial U by partial Y square, which makes very sense because the velocity is changing vertically between the two plates in the Y direction. So the energy equation will end up to be lambda partial 2T by partial Y square plus mu partial U by partial Y square equal 0. And this is where the temperature and velocity are coupled here. So we're going to need the velocity distribution equation to get the first derivative. Then we can substitute to get the temperature distribution here. So I hope you guys can see the coupling between the hydrodynamics and the energy equation here. So let's go that route here. So I'm gonna go and okay, I have U as a function of Y is equal U capital over H times Y. So partial U by partial Y will be simply U over H. Remember, U and H are constant values. So I can take that into this equation. So I can say that partial 2T by partial Y square will equal mu over lambda, and partial U by partial Y will be simply U square over H square. So I have mu U square divided by lambda H square. Just as a reminder, lambda here stands for the thermal conductivity, right? So I got that equation here. I think we are missing a minus sign here. This term is going to go to the right-hand side, so I'm going to have a minus sign here. So I have minus mu U square divided by lambda H square. Let me multiply by Cp divided by Cp, where Cp is the specific heat. And let's see what we can do in here. Mu Cp over K, this is Prandtl number, right? So the Prandtl number is defined as mu Cp over K. So I can combine this term, and this term, and this will give me the Prandtl number. So I will end up having minus Prandtl number U square over H square Cp. Okay, then now I can actually get the integration twice of this equation. This is partial 2T by partial Y square. These are all constant. I can integrate twice to be able to get the temperature distribution as a function of Y. So I will integrate once. I will get partial T by partial Y will equal to minus U square Prandtl number divided by H square Cp. Then I will have Y plus C1. Then I will do the second time integration. I would have T as a function of Y, that's what I'm looking for, equal minus U square Prandtl divided by H square Cp. Integrating Y is going to give me Y square over 2 plus C1Y plus C2. Let's draw the schematic of the problem. This is a two parallel plates. This is Y equal 0. We define the temperature of that lower plate to be T naught. Then this plate is at Y equal H, and we define the temperature of that upper plate to be T1. So now I need these two boundary conditions to be able to solve these constants C1 and C2. So at Y equal 0, T at Y equal 0 is known as T0 or T naught. At Y equal H, the temperature at that location is given by T1. So these are the two boundary conditions. Let's substitute into this equation by the boundary conditions so we can actually find the constant C1 and C2. So if I use the first boundary condition, I will put Y equals 0, Y equals 0. So I will get from here T naught is equal C2. So I got the first constant very quickly here. Then I will go for the second condition. I will call T1 equal to minus U square, Prandtl number. Then this is going to be H square because I take Y equal H, divide by 2 H square CP plus C1 H plus C2, which is T naught. H square will cancel out. So T1 equal minus U square, Prandtl number over 2 CP plus C1H plus T naught. I can isolate C1 from here. So T1 minus T naught, T1 minus T naught. Let's do that divided by H plus U square Prandtl number over 2H CP. This will give me C1. Okay, so what I did, I brought that T naught to the left-hand side, so T1 minus T naught. Then I'm going to divide by H, all terms. So this will be divided by H. Now I have U square, Prandtl number divided by 2CP and H that's coming from division here. So I got C1, I got C2. I can go back and substitute into the equation to get the temperature as a function of Y is equal to minus U square, Prandtl number divided by 2 H square CP, that's Y square, plus C1, it's T1 minus T naught divided by H plus U square Prandtl number divided by 2H CP. This is totally multiplied by Y plus C2, which is T naught. Okay. Let's distribute that term here. Then we're going to simplify the equation in an easy way. So T as a function of Y equal minus U square Prandtl number over 2H square CP Y square plus, I'm going to call T1 minus T naught. Keep it that way right now, but we're going to remove that and call it delta T later on. U square Prandtl number over 2H CP, that's Y, plus T naught. Let's call T1 minus T naught, let's call that actually delta T. So T as a function of Y minus T naught divided by delta T. What we're going to get? I'll get, this is delta T. I will divide all the terms by delta T. So we'll get the following. We got minus U square Prandtl number over 2H square CP, that's delta T, Y square plus Y over H. Remember, delta T is gone from here. I divided by delta T, so it came here. Then plus U square Prandtl number divided by 2H CP, and there's delta T, and this is time Y. So T naught came to this side. Then I divided all the equation by delta T. The reason I've divided by delta T is to define a new dimensionless number. It's called Ecker number. And Ecker number is defined by U square divided by CP delta T. Ecker number is the ratio of the kinetic energy to the heat transport. Is if you have a heat transfer going from the lower plate to the upper plate or vice versa, competing with the kinetic energy that carry that heat, that's the Ecker number. So Ecker number can be written as E T. So it's going to be U square over CP delta T. So U square over CP delta T, that's Ecker number. U square over CP delta T, that's Ecker number. So this equation can be written as T as a function of Y minus T naught divided by delta T. Keep in mind, delta T is the difference between T1 and T naught, equal to minus Prandtl number, Ecker number, divided by 2H squared. that's y squared plus y over h plus Prandtl Eckert number divided by 2h y. So I can rewrite this minus Prandtl Eckert over 2 y over h square plus y over h plus Prandtl Eckert number divided by 2 y over h. If I take half Prandtl number, Eckert number as a constant, what I'm going to get? I'm going to get, I took that, I will get y over h. Actually, let's take y over h also outside. So this will be simply 1. I took half Prandtl Eckert y over h as a constant, as a common factor. This will be 1 minus y over h plus y over h. This is t of y minus t node divided by t1 minus t node. And this is will give me the temperature distribution. This is a temperature distribution in the fluid between the two parallel plates. If you usually if you try to plot this equation here, if we call that dimensionless number, let's actually simplify the equation. If we call that theta of y is equal the ratio of t of y minus t node over t1 minus t node. Then I called y over h, I called that x or z. So this equation can be written as theta as a function of y is equal half Prandtl number, Eckert number, x 1 minus x plus x. So it seems like if you want to plot the temperature distribution here, the dimensionless temperature, you need the combination of Prandtl and Eckert number. Again, remember, Prandtl number is mu Cp over K, and Eckert number is U squared over Cp delta T. These are the two dimensionless numbers. So usually we plot this equation as follow. If you look to the two plates here, T node is the lower plate temperature. And T1 is the upper plate temperature. U capital is the velocity here. So theta, the dimensionless temperature ratio, is mainly a function of Prandtl time Eckert number. So for example, if you put Prandtl Eckert is equal 0, you will find that temperature distribution will come linearly. If this is 0, the whole term goes away, and you'll end up having theta is actually equal y over h. So it's going to be linear distribution, right? Remember, so for example, let's write that down here. If Prandtl Eckert equal 0, theta of y will be simply equal to xi or x. So t as a function of y minus t node divided by t1 minus t node will equal 1 over h times y, which means that these are all constant here, so you can actually see that this is a linear equation. So this is if the combination of Prandtl time Eckert equal to 0. If you change that percentage, you will start getting a parabolic profile. So this is, for example, if that value is equal 2, 4, 6, the more you increase that term here, this is showing when you increase that term, the Eckert number effect increase, right? If mu is constant, Cp is constant, K is constant, so actually Prandtl number is not really contributing too much in here. It's going to have a fixed contribution every time. but the Eckert number is a game that's function of the velocity u, right? So the bigger the Eckert number, it's indicating the higher of the kinetic energy. That's why temperature is dragged a little bit more. The profile is dragged a little bit more to the parabolic term here. So this is just a quick example showing the coupling between the hydrodynamics and the energy one, and showing that really the three conservation laws are very important to be solved together, and how we use the results of the hydrodynamics from the momentum equation to be integrated into the energy equation to be able to drive the temperature distribution between the two plates. Think now if the two plates are fixed, like Poisson or Boisel flow, pronounce it the way that you feel comfortable with. But yeah, you can change the boundary condition, but you can still drive both the velocity distribution and the temperature distribution. So this here exercise is concluding the use of the conservation laws to get the analytical solution between two plates or Couette flow with temperature gradients between the two plates. So the question is, can we solve that numerically? This is the analytical solution right now. Can we solve that analytically? And this will be covered in my next step. I'm going to solve the same problem numerically and see if we can actually compare the analytical solution to the numerical solution here. You have seen that how the analytical solution requires you to drive velocity profile, then you implement that into the energy to get the temperature distribution. Does the numerical simulation or solution or approach will require us to go the same hard way? That's what we're gonna see in the next exercise.